Okay, so in the last class, we were here, right? So we were discussing like how face recognition and smile shutter, techniques which are already incorporated in these high DSLR cameras, how it is working actually. And we saw that internally, object detection algorithm is running, and object detection algorithm can be implemented as a classification problem also. So as you can see here, we have this phase and non-phase, and I told you that how to do this. So it's a very high level overview. So do not worry how it is happening. We will explain you as we progress. But this is a general overview of what classification problems look like. So again, this is the same block diagram which came earlier also. I will explain this in detail in the today's lecture. So please keep this picture in mind, and we will discuss this in details in the next slide. So do not worry about it. And same thing goes with this particular figure, which is showing you a cost function. So do not worry about all these terminologies. I will discuss all these details and diagrams today. So once we reach at that point, I will show these figures again, so that there will be a correlation between these slides and the slides which I will show you in the coming lecture. Okay, so supervised learning algorithms basically will be categorized in all these different algorithms which are listed out here. So one is the linear regression, then we have logistic regression, then we have KNNs, support vector machines, and decision trees. So all these are jumbled, all these are categorized into supervised learning algorithm, and we will be discussing each of these algorithms in detail, and the whole course will be relying on these algorithms, how to go into the detailed understanding of all of these. So we will discuss all of these algorithms as we progress. Okay, the other learning algorithm which is existing is, yes.
Sir, sorry to interrupt, sir. Recording is not on, sir.
Oh, just a second. No, it's already on. I have already activated it. Okay.
Okay, sir. Okay. Thank you.
Okay, so now the second kind of learning that we have other than supervised learning is unsupervised learning. In unsupervised learning, what happens is we have an automatic learning of computational rules that describes the input data only. So what it means is that earlier we, as I told you, in supervised learning we have this data X, and we have the corresponding labels Y corresponding to it. So if it's a cat image or dog image, we actually attach the labels to the corresponding images. Like for example, cat images, if I say the label attached to it is 0, for the dog images I am saying that the label is attached to it as 1. So in supervised we are actually giving information to the model which we are learning, and this information in terms of the extra knowledge is coming through these labels. So we have this 0 for cat, 1 for dog. But right now, in case of unsupervised learning, this information will not be given to the machine learning model. So what unsupervised learning will be doing is it will try to learn by the by the images itself and form a cluster. So it will try to form a cluster by itself, so that it can distinguish the cat images from the dog images. But in these type of learning, there will be no labelings attached to the images which we will be training. So if you see here, what we are trying to do is we are actually giving this model letters composing of A's and C's, and you can see the A's are of different orientation and C's are also of different orientation. And note that we are not providing an extra information to these models. If you recall, in our earlier slide, we provided an additional information in terms of Y, but that is not here. So what will our model do? It will actually try to separate these separate this single bag into two bags having A's and C's, so that if you do a testing on this model by providing a separate image to this model, then the model will actually try to put this in this bag. Or if it is a C, a different C which is not there in this training model, so this C, once it is fed into this model, it will put it in this bag. So basically, this is unsupervised learning approach where labels or extra informations are not provided for this model. So in this category, we have clustering and dimensionality reduction algorithms, which we will see once we go further down the lectures. But dimensionality reduction, if I want to explain you in a very simplistic term, it is basically how to project the data into lower dimension space. So here, if you see this particular data which is over here, this particular data, these dots which I am showing you, these dots are basically represented in a two-dimensional feature space, for example f1 and f2. Then what we are doing here is we are actually projecting this data onto this line. Here also we are projecting the data onto this line, and once we project this data onto this line, we can take this line as the modified feature space, and we can call this as, let us say, x1. So now what is happening, from the two dimensions f1 and f2, you reduce the data by projecting onto this line, and this line is having only a single feature x1. So you are reducing the dimensions of the problem. Earlier the dimensions was 2, and now the dimension is 1, because all the feature points are onto the line itself. So this is called as dimensionality reduction algorithm, and it helps us in doing various jobs which we will see in the coming lectures in future. But this is just showing you what this dimensionality reduction algorithm will do in nutshell. And similarly, this is showing you a 3D space point projected on a 2D plane, because it's a plane, right? So it's a two-dimensional plane. So all these data points will be in two-dimensional plane, which are residing on this plane, whereas this is basically a point corresponding to a higher dimensional space, maybe 3-dimensional space or 4-dimensional space or 5-dimensional space. So you are projecting it onto a lower dimension space, which is the points which are lying on this plane. Any questions? So we will see various algorithms which lie in this category of dimensionality reduction later on. And another algorithms which we will see in the unsupervised category is clustering, which we were discussing just before this dimensionality reduction algorithm. And you can note here that the data points which I am listing out here, there is no labels attached to it. And also note that the colors of these dots are same. They are not different. In case of linear regression, we had some information available. So at that time, we had some coloring of the point, but here, there is no coloring, which indicates that the labels or the extra information is not given to it. So when the extra information is not given to it, so the thing is, they are all shown with the same color. So what is our target? Our target of clustering algorithm is to actually form clusters. And you can see here, once you feed this data into the clustering algorithm, the clustering algorithm will output this type of results. And here you can see we have a cluster formed by these blue points, and the cluster is formed by these red points. So what happens is, clustering algorithm tries to find a relation, like how close these points are together with each other, and they try to form a cluster across it. And these points are far away, so it will be segregated into a different cluster. Similarly, here we have another data set which is represented over here. You can see that in this case also there will be a one cluster which is formed like this, and another cluster which is formed like this. So the key takeaway point here in clustering algorithm is that the labels will not be provided to you. It will be automatically, basically the algorithm has to automatically find out which cluster, which images are can be clustered together into a single cluster. So this is basically clustering algorithm, which we will discuss later on in more details. Okay, another learning which we have is semi-supervised learning. So in semi-supervised learning, what happens is our data in which we are dealing with are partially labeled training data. By saying partially labeled training data is some of the data will be unlabeled and some of the data will be labeled, and the data which is labeled is very less compared to the lot of unlabeled data. So can anyone tell me where we can find these type of situations? Can anyone tell me this? Anyone? Am I audible to all of you?
Oh, yes, sir.
Yeah, okay.
Yes, sir.
So these type of situations actually happen in real practical situations. It's like, it's a very practical situation, because as I am doing some projects with some of the government organizations, so I don't want to name them, but some of the organizations, what their main heads are telling is like, the people who are employed in doing labeling of the data, they are leaving some portion of it and they are putting some portion of it. So the thing is, because of the carelessness of the employees who are not putting the data properly in the Excel sheet, this type of situation will happen. Some of the data will not be labeled because of their carelessness, and some of the data will be labeled. So at this type of situation is a very practical situation, and this type of situation is actually coming in semi-supervised learning category. And note that we will not be going into the study of this because it again requires a separate course. So we cannot deal with this type of learning approach because it's a separate treatment. So somewhere in the future, if maybe I will float this course later on, but now for this particular semester we will not be focusing on this particular learning. But this is the more practical way of doing the stuff. Again,
Sir,
yes.
does the camera on the traffic signal, on the signals,
Hmm.
example of this,
Camera on the traffic signal.
which detects whether you are breaking a rule
See, the thing is,
or
see the camera which is installed on a traffic signal and which detects whether you are breaking a rule or not is actually built on uh, already on an algorithm which can do this stuff, right? So at that time, the data set which they are providing for this is already labeled properly. You understand? They have already labeled that this particular car will belong to this particular company and all this type of stuff. You understand? So these type of situations, like detecting the car in the traffic signal and whether they are breaking the rule or not, it's already trained on the labeled data set and not on the unlabeled data set. Okay, and once they are trained, then they will use it for practical purposes. Okay, is
yes,
it
sir.
okay? Okay. So now this is again one of the practical ways of solving the problem, and we have several algorithms related to it. And if you wish to pursue in this area, then you can please look into the details later on because there are chunks of videos available. So maybe you are free to watch them in case you are interested. Another area which requires a separate treatment is called as reinforcement learning. So this is actually the one of the learnings which is close to humans. So right now I'm not teaching this particular learning course, but maybe in the coming semester or next semester I'm trying to work on this and will float these lectures later on. But this particular reinforcement learning is actually very close to the human learning. So the way human learns, it will actually this learning is actually mimicking that, and none of the other learning techniques which I have discussed in the above are close to the methods which we use in reinforcement learning. So though we say crudely that supervised learning is close to human learning, but it's not. Supervised learning is not close to human learning. It's only the reinforcement learning which is very close to the human learning. Let me give you a brief introduction of what this is, just to bring interest in your so that you can if you want to understand this particular area of reinforcement learning, you can try to go for some blogs or can understand from various internet resources. So what happens is, in the reinforcement learning we have a concept of agent. So agent is nothing but a person, or it can be anything. It can be a robot also, or it can be a child who is learning various things as he progresses in life. So agent can be either of these two, and which basically wants to learn. And environment is everything other than the agent. So if you consider a case of a child, then child is basically an agent, and whatever child sees around him or her, it is an environment. So if a child sees an apple, so apple is actually considered as an environment. And if a child is roaming on floor, and he is seeing several other objects present at home, so that several objects which are present at home, like TV, refrigerator, and various furnitures, all that will be constituted as an environment. So what happens is, this particular agent, right now I will call it as agent, neither robot or child, so you can understand what I am trying to say when I call agent. So what agent is doing is, it is basically performing some action. So let us say, if a child sees an apple, so it will try to grab it. So by grabbing an apple means it is taking an action to pick up that apple. So once it grabs that apple, it is taking an action. And what will happen is, then environment will actually react onto that particular state. So what happens is, when a child grabs an apple, it is okay for him. So he or she will like it. Maybe he or she will eat it. So it will be a fruit which is very ripened. So he or she will be happy in that. So what will happen is, environment is actually giving a reward. So environment is actually giving a reward in terms of the sweetness of the apple. So the agent will feel happy actually. So when he or she will eat it, so he or she will be happy. So that is in terms of the reward. So once the reward is gained, what will happen is, environment will give a new state to this particular agent. By new state means, let us say the agent moves to some different object. So that is a new state which is given by the environment. So the new state will be that the child will move towards some different objects. So let us say it goes to somewhere near to the fire. So if it goes near to the fire, what will happen? Suppose the agent will do that same activity again. That is, it will try to touch the fire. So when it tries to touch the fire, it is taking an action in that state. And the state is, it's a fire state. So agent tries to touch that fire, and what that means is, it taking an action. So when it touches a fire, what will happen? His or her hand will be, it will get burned, right? So once that happens, the reward is now negative. Earlier the reward was positive. Now the reward is negative. Because fire is creating unnecessary troubles to the agent. So agent will not be happy by touching the fire. So we provide a reward of negative value to the agent, because agent has done something wrong. So what will happen? Agent will learn that whenever he or she will see the fire again, he or she should not touch the fire again, because last time it has been given a reward of -10 for that. So in this process, like giving a positive or a negative reward is basically providing these agents an experience that they should not, or they should do some activity depending upon the type of reward they are getting. So if it's a positive reward, agent will try to do that same activity again. But if it's a negative reward, agent will try to avoid to do that activity. So by this, getting the reward and getting new states and touching and getting and taking actions in that particular state, all these interactions between the agent and environment keeps on going till the agent actually learns how to play in this environment. So normally most of the robotics which you will see, if you want to take any course on that, that's a different story, but most of the robotic concepts, like how robots move around in the environment, is basically reinforcement learning algorithms which are running in their back end. So this is actually the real state of the art learning, which closely relates to human learning, and most of the robots use this. So we are not going into the details of this, but because of the because this particular course requires, this particular topic actually requires a separate course for this. Any questions here related to what I have discussed?
So, what do you mean by state of the art?
State of the art?
Yes.
Did I say that? State of the art nahi. What I was telling is, this agent is in a particular state, and then it moves around, and it gets different states. But what I am saying in terms of the state of the art, if I was telling you this word, what I meant is reinforcement learning actually is the latest learning approach. It's a latest learning approach which is closely mimicking a human behavior. It is not the supervised learning which is mimicking the human behavior. It will do it for part of it. Like it's a very approximated way of doing basically reinforcement learning. You can say it's this set, and basically your supervised learning is as a subset of this reinforcement learning, and it is very small. So reinforcement learning is the current state of the art, in the sense that most of the people, if you want to implement the real applications of robotics, as well as some games, if you want to deploy on real platforms, so all these real applications basically require reinforcement learning to do so, and it's not supervised learning. Okay, that is what I meant. Okay, any questions? Okay, so if there are no questions, so let me start with the new topic here. So from here, whatever things will start from now, you have to document it. So this is the point where when I'll assign this to a particular group, then they have to write from here. So this is the point. This is the starting point from where they have to document the stuff. Okay. So now this is the typical machine learning pipeline which I have shown here. So let us see each individual blocks, what they are trying to say here. So this is basically the data which we have, which we want to use for our machine learning task. So in case of cats and dogs, it will contain images of cats and dogs, and we are actually writing it in this form. So it's a cuboid which has lot of images inside, so we are just depicting it in a graphical sense like this. So it has all the data, and we are calling this data by X. Now the second important thing is to extract the features, and extracting of the features I have already explained you in our last lecture. So what it tries to do is, it actually tries to gather useful information from this data, which is actually required to separate these cats and dogs. So we are trying to find an intelligent function phi operated on this X. So this xi operated on this X is trying to find a intelligent transformation of X into psi X, so that this intelligent transformation can help us in separating the problem of cats from dogs. Okay. Then we have this prediction model. This prediction model is nothing but the machine learning model M, which we denoted last time. So what is this machine learning model M will do? It will actually try to come up with this intelligent function f, which operates on these features phi x. So this is the function f, which is an intelligent function which this machine learning model will come up with. And we already know that this f of phi of x will give you some predictions whether it's a cat or a dog. So if you feed some different phi x here for a different image, a test image, if you have this test image, you will take the corresponding features of that and you will call that as phi of x, let us say, and then you operate f on that, then you will get the answer whether it's a cat or a dog. So our target here in this prediction model is to come up with the intelligent function f, which can separate in between the two classes. Okay, so now once we have this f of phi of x, what will happen now is we also have the ground truth labels which I have already explained you, and we are calling it as by y. So this is the ground truth label we have already, and then what we are doing, we are actually feeding these losses, feeding these two evaluations into a loss function. So this we do not know what it is, we will explain you today in this class. So this is the loss function which is denoted by capital L. And what is this loss function? We will explain you later, but it requires two arguments inside it. One argument is f of phi of x, another argument is y. So this is the two arguments which it requires to calculate the loss. And what is the objective of the loss function? The objective of the loss function is to calculate the difference between the two. So it will give you a value if f of phi of x is different from y. So it is, if it is very different from y, then it will give you a very large value. And if f of phi of x is very close to y, then it will give you a very small value. So it is basically trying to do a distance calculation between these 2 points. One is f of phi of x and y. So it is trying to see whether f of phi of x is very far from y, or is it very close to y. So it is giving you the corresponding this distance measure using this loss function. So it is nothing but it's a distance sort of thing. It tries to capture the difference in between the model prediction and the actual label. So what happens now is this loss function will be used in another block which we call as optimization block. This also we will discuss once we move further. But this block, what it will do is, this optimization block will try to tune this model. Sometimes it tunes the features also, but right now in this course what we will do is we will actually use this optimization model which takes this loss function, and what this optimization will do is it will tune the model. It will tune the model to come up with the better function f. So as you train, continuously you train, what will happen? Optimization will keep on training the model also, and by training the model means it will train the function f so that f becomes better and better as you train more. So the training process basically happens in this particular stage. This is the block which actually helps us in doing this. So optimization will actually train the parameters of the model. So I can write it like this: optimization is basically helping in training the parameters of the model. We will see what these parameters are for the model, but you should keep this picture in mind when we will discuss the topics of machine learning. So whenever I say I am writing a model, means your brain should immediately come to this slide, and you should be comfortable that if I am writing a model, then I am actually at this stage. If I am writing the loss function, then I am actually at this stage. If I am writing an optimization framework and if I am doing some optimization strategy, I am at this stage. So you have to keep this picture in mind, because as we progress, we will continuously use all these terminologies which are given over here. And you should know that at which point these descriptions are, like, if I am saying loss, so what will happen is you should immediately realize that loss function will take two values, one coming from the model, another one is the true label. And you can anyone tell me why you take these two as the input? What is the requirement? Like if I feed this and this, what it is trying to do here? Can anyone tell why this loss function is actually using this and this only? Why not something else, like, why not this only?
So because the loss is calculated by subtracting from the actual value from the predicted value from the actual value.
Right. So basically the actual value is y. If you say actual value is y, and the predicted value corresponding to that is f of phi of x. So this f of phi of x is nothing but it's a predicted value which you can call as y hat. I'm saying it as a y hat because it is different from y. So if y is, let us say, 1, it might be the case your y hat is, let us say, 0.98. But actually it has to be 1. It should not be 0.98. So what we do is we actually create a loss function corresponding to this difference, and whatever value that comes, we backpropagate the errors. We backpropagate the errors in this optimization block, which tries to tune this f in a much better way, so that next time this 0.98 will become 0.998. And then we keep on continuing this so that it becomes closer to 1, so that our loss function becomes 0. So this is, yes. Yes.
Sir, there is an arrow between optimization and extract feature as well. So will it also improve extraction of the
Actually, it can be done, but for this course, it's not required. But it can be done. You can use this optimization for extracting the features also. Okay. Okay. So I hope everyone is comfortable with this pipeline. Then if you do not have any questions, I will move further now. So now we will discuss one of the algorithms, the first algorithms in machine learning, which we call as linear regressions. So here I am showing you a data which is given over here. You can see we have year on the x-axis and the winning time on the y-axis. So it's a winning time of the Summer Olympics by the runners. So whosoever has had a winning time, that time is plotted over here, and you can see that as the years are progressing, each and every year, whenever it is this Olympics is happening, the runner is breaking the earlier record. That's why the time is going down instead of going up, because otherwise there will be no point in plotting the data, because winning time is always like breaking the records of the earlier also. So somewhere it's like it's following this downtrend, because winning time is also decreasing as the years are progressing. Okay, so what is our objective here? Our objective here is to predict the winning time at any time. Like if I want to predict the time here, winning time here, if the data is not available, I want to do that. So I want to predict what will be the value here or what will be the value here. So if I want to predict that, it should give me the result corresponding to it. So we want to do this type of analysis, and note that whatever data is available here, this is actually a training data. This is the training data which is available to you. And in testing, if I, let us say, want to predict the winning time for this particular year, then note that this particular year for which I am predicting, it should not be in the training data set. It's a test data set. It's a test data set. And for this test data set, I want to know what is the winning time in this particular year. So in order to do this type of analysis, what we want to do is we want to first of all visualize this data, that how it is looking, if it is possible for you to see so. So if the data is very complex and you cannot visualize it, then we have some other algorithms for doing so. That is, we use neural networks and all other advanced architectures for this. But for simplistic data, what you can see is you can visualize this data and you can clearly see there is a downward trend in this data. So there is a downward trend in this data or not? So we have this data going down as the years are progressing. So what kind of model you will be using here? Like anyone? Can anyone give me the idea like what kind of model we can use here? So no. See, the thing is, first of all, the important thing is to get this model M, right? We want this model M to be there. Then only we can do this prediction, right? So, okay, let me tell you this. So, as you can see, yeah, yes.
The least square.
No, least square will come later. What I am trying to describe is the model actually, which a model which takes input and gives you some output. So I want the definition of the model. Can you tell me what kind of model I can put here? So if, let us say, if I put a straight line like this, will you all agree that this is the perfect model for this type of problem?
Yes, sir.
Right or not? So because you can see there is a straight line. So what, by observation I saw that there is a downward trend in this in this data point. So let us fit a straight line passing through it. So this is basically called as model. I will discuss more about it in coming slides, but for now you just keep this in mind that by observing the data we try to find a hypothetical model for us. Why we have not taken this like this? Why we have not taken like this? Some model, some arbitrary model like this. We have not taken this arbitrary model because we cannot see any data point here. So there is no winning data point this side, right? So if there is no winning data point this side, so we are not using this as our model. And other option for putting the model is, you can use this also. I will tell you that, like this. You can use a model like this also. Something like this. But again, it has some problems which we will discuss later on, but these models are not, a perfect model for, for fitting these data, because we do not want to fit the data at each and every point. It leads to overfitting problems. So we will discuss this when we go further. And it's also very difficult to actually write the mathematical expression for these curves. So if I draw this curve, let us say like this, let us say I draw a curve like this. So it's very difficult for me to write the mathematical equation for this model. So all these things, are difficult to do. So that's why we try to approximate with simpler mathematical functions which can help us in defining the model simply. Okay, so that's why we use a straight line, because it's a very simple model, and we can use coordinate geometry to write the equation of this straight line. So what will be the equation of the straight line? Can anyone tell me? Anyone? Yes. So we can use the equation of the line as y is equal to mx plus c. Very simple, right? And for this particular line, your slope will be negative and you will have some intercept. We will see how to play with this. But the important point is, rather than taking a complex model which is very difficult to define, it is better to go for a simplistic model which can help us in predicting the data points. So let us go further into this problem and see how we can do that. And before going further, let me describe some mathematical notations for this particular course, which will remain throughout the course. So understanding these mathematical notations are very important. So right now, this data point which I am showing you graphically, the corresponding data points for that is given over here. This is the corresponding data points. So for the people who will be drafting this lecture, please note, it's not necessary to use this particular image for your explanation. You can use any image from the real data sets. So it's not required to keep this one only. But please note that the concept should be simple. It should not be something like this. You have to take the example which can have this downward trend or an upward trend. It depends upon your application, but take the example of a simplistic case, not the other cases. So not required to put this only as the example. Okay. Yeah.
Do we always have to visualize the data before deciding?
Yes,
what we want?
it is important to do that. If it is very hard to do it, then we have other advanced models to do it. But it is really one of the best ways to go further in understanding machine learning and do data analysis, and that is by visualizing the data. First of all, you have to do that. So here you see we have these data points corresponding to this particular curve, and note that we are using some terminologies here to denote these data points. The first one is I. What is I? I is basically nothing but it's the number of samples which are there in this particular data points. So we have 27 samples, so our I is actually running from 1 to 27. So this is basically total number of samples that you have for a problem. Then we have X, which we are defining over here. It has two parts. One is superscript and another one is subscript. The superscript is actually telling you which sample you are looking at. So by, let us say, if I say X, let us say 5. So what I am doing is I am actually looking at fifth sample and the X feature for that. And if I specifically say X5 with the subscript 1, then this one is actually nothing but it's a feature which is available here. So right now we have single feature, so that's why we have only one here. So this X, so if I write X5 with the subscript 1, that means this is the first feature and the value of that is 1908. First feature of fifth sample. And if I say X19 1, that means first feature of 19th sample, and that value will be 1976. So let us say if you have multiple features, so for example, if I draw one more one more column here in this Excel sheet, and if I write xi2, then it means ith sample, the second feature of that ith sample. So if I have x, let us say 22 second, then what I will write? I will write this 22nd samples second feature, which will be this one here at this point, if it is there. So this is basically a generalized expression for that is this, where you have x superscript I subscript n. N denotes the features. Right now in this problem we have only one feature, so n will be 1. So this is regarding the feature representation. How will you represent the features? Now we have labels. Labels are represented by y superscript y, I. So the labels are represented by this, and you can see that if you want to get the labels for, let us say 12, so what it means is you want to know the label of the 12th sample. So you have this 12 and the corresponding label to that is 10.30. Is it okay? Any questions here related to this? So I have given a small example also corresponding to it. I think it is evident now how to get these values. I have given examples here with the different values, but you can cross check. Like if I ask you x14 then it will be 1956, and if I ask you y14 then it will be 10.5. This is given over here. So we will be actually using these terminologies for our machine learning algorithm. So keep this in mind, and a set of xin, yi will form a training data for us. So if you recall this particular thing here, this data which I was telling you, this data is nothing but it's a set of xni and yi, and we call this as capital D. It's a training data for us. Okay?
Sir,
Yeah.
if we are just given this CSV file with these numbers or values, so do we have to extract a few values for testing?
No. In testing, what happens is, that's what I was telling. In testing, what you have to do is you have to actually split this into some ratio, 80-20%. 80 20%. Okay, and make sure that this 80 20 is, there is no overlap in between. Okay, so if it is 80, the rest of it will be here. Okay, so 20% 80% like this. So you have to keep this separate for testing data.
In this case, this is sorted and also. So do we have to take it from somewhere in somewhere 20% values or 20% random values, or we have to take 20%
See,
values?
there are two ways of doing it. There is no need of sorting the things. There is no need of sorting the things. That there are two ways of doing it. One is, what happens is normally people, what they do is they take 80% like this. Randomly, they will take 80 here and 20 this side. You can take 20 here and 80 this side also. There is no problem. You understand? So what happens is sometimes there is another way of doing this testing. What they do is they create something like this. I will tell you this. Just a minute. So you have this data set. So what they do is they take 80% training and this set as testing, which is 20%. Second time when they will run, what they do is they take this part as testing and this part as training. Then again they will run. What they will do is they will use this particular part as testing and the rest of the part, which is 80%, combine these and this, it will constitute 80%. So this they will use as testing. So they keep on doing it for different parts and finally they average out the results. Okay, this is another way of doing this, but there is no, I hope you get the idea, right?
Yes, sir. Yes.
So
But sir,
yeah.
if the values are not sorted, then wouldn't it be difficult to find the pattern from the data?
Sorted in what sense you are saying?
Sorted means if values are not sorted, then the points will be very much scattered. So isn't it will be difficult to find the pattern out of that?
I don't think so. There is no point in sorting the data. For what sense we will do that?
Sorting in the sense means, sir, if the data is so much scattered, like in this example, as you can see that data points are not that much scattered. But if the data points will be very much scattered, then it will be hard to find out a pattern from it.
Normally, what people do in terms of sorting is doing some data transformation. So let us say in this particular example, you can see here we have our data which is in the range of thousands, right? And here you have data in the range of in tens, like 10, 9, 8. So there is a variation in the range. So because of the variation in the range, sometimes it happens that data will be scattered at that, skewed or somewhere located at some specific point. So what we normally do is we normalize them into the same scale. We keep them in same scale, like we keep this and this in same scale, like this also in between 0 and 1, this also in between 0 and 1. So both of them will be on the same scale, and once you do that, what happens is data becomes sorted out and it becomes more pictorially pleasant, and it's easy to perform gradient descents and all other optimization algorithm which we'll discuss later on once you bring them onto same scale. But I have never heard about sorting the data. I cannot recall like what you are trying to ask me on that.
So,
But
no, sir, I get that by
Okay.
this example,
okay.
which you said just now.
Okay,
Okay, sir, thank you.
thank you. Okay, so this is again showing you the same story but with the different plot. So what we have is we have the training data, then we have a learning algorithm, and we are feeding this into this learning algorithm so that we can come up with this model M. And now once this model M is available with us, we can feed the testing data into this model to get the prediction values. But now the question which comes by looking at this slide is, how do we represent this model M? So now this question comes in relation to when I was telling you how to actually model this particular line. So this question will be answered now. So now what we will do is we will try to come up with the model representation of M. So right now I am taking a very simplistic model, which is this one. So anyone can ask me like why you are taking this only. So there is no constraint on it. The first reason for selecting this is by observing the data, and we saw that there was a downward trend, or maybe if it's an upward trend also, the same model will be holding up at that point also, because the important point that we have observed is the data is close to a straight line. So let us fit a straight line here. So that's why we are taking this as the model. We could have taken another model also. Let us say theta 2 xi 1 square. We could have taken this also, and this will bring in the quadratic term also along with this model. But we have not taken this because we are not seeing any quadratic type of activity here. We are not seeing anything like like this, as I was telling you earlier. So by observing the data is very important. At least you will get to know which type of model you want to fit. So because there is no quadratic behavior, we will not be using this. And note that this particular problem has only single feature, so we are writing 1 here, and we have xi. I corresponds to the sample points, and this model I am representing by this terminology, which we are calling as m theta xi. So this is the model. Okay, so now we have this theta 0 plus theta 1 xi, and if you look closely, it is same as mx plus c, where m is nothing but theta 1 and c is nothing but it's theta 0. So it is similar to that, but I am writing it in terms of theta 0 and theta 1. Now the important thing that I want to discuss here is that we are calling this theta 0 and theta 1 as the parameters. So note that these are the parameters which will be adjusted by the optimization algorithm. So if you recall here, what I was telling, this optimization algorithm will try to adjust this model, and it will come up with the new function f, so that we'll get the better accuracy. So optimization will actually use to adjust the model of the parameters, and that model I have written here, right? Training the parameters of the model. So the parameters of the model are nothing but this theta 0 and theta 1. So if I change this theta 0 and theta 1 continuously because of the optimization technique which we will discuss later on, then will you all agree that the line equation will change, and this will change the intercept as well as the slope? Will you all agree on that or not?
Yes, sir. Yes, sir.
So this is actually shown on this slide. On the left side you can see, if the optimization algorithm changes the theta 0, which is the intercept, then you can see the line will change like this. It will change like this with the increasing value of theta 0. But if the optimization algorithm is changing only the theta 1 and keeping theta 0 constant, let us say to 0 value, if I substitute theta 0 as 0, then what will happen? It will change the line like this. So you can see this is a simple coordinate geometry, right? By increasing the value of theta 1, your line will actually change like this. So what happens is the optimization algorithm will tune both theta 0 and theta 1 together. Then you can clearly understand that the line will change in the slope as well as in the intercept, and it will change continuously till it fits to the data properly. So our optimization algorithm will try to tune these theta 0 and theta 1. We will see how it will do that, but for now, if you have any questions related to what I have just told you, you let me know.
Sir, one question, sir. You said that we can't see any quadratic over here, so activity. But sir, if the polynomial's degree is even, then we can then we would clearly able to see that there is a parabola. But sir, if it's odd, how can we predict that degree? Because it will just have curves, but it will not have a parabola.
Good question. So the problem is, see, in this particular case, what I have done is I have just taken a simplistic model of linear regression. You might have taken this also. Let me show you that. You might have taken this also as one of your models, and there is no harm in doing that. So there is no harm in using this kind of polynomial. So if you use this type of polynomial, then you have to use a model looking like this. That is theta 0 plus theta 1 xi1 plus theta 2 xi, let us say, the important thing is, in this particular case, you can only have, a variations like this only, x1 I cube. So all these are polynomial features, right, in relation to xi1. So what happens is you can actually use this type of model also. But the important point that I wanted to discuss, and which will discuss later on when we will go into deep in the machine learning, is that we cannot unnecessarily use a very complex model. So that will actually that will be okay also, but the problem is it creates some overfitting problems. I don't want to term them because right now it's too early to discuss overfitting and all these type of things, but we will discuss this later on. But you can use any arbitrary degree polynomial to fit this line, so you can use it. But the problem is something else will try to create problems for us later on. So we do not want to go into the details of that now, but the important part is to keep the model simplistic enough so that you can capture the data properly. Okay. These things will clear as we progress further later on down the course. Do not worry about it. All these things are important issues which will be addressed once we go down there. Okay. And if you still want to look into the answer of this, you can look for overfitting, regularization, all these concepts. They will try to address these type of issues. Okay. Okay, so now from here, as we can see, the optimization will actually change these theta zeros and theta ones, and if both of them are changed, then you can observe that your line will actually either it will rotate as well as it will shift along the intercepts. So you can see now how we can model this m theta xi and how we can adjust this m theta xi using this equation. And note that I am writing subscript theta, which indicates that these theta is the parameters of this model, which are denoted by theta 0 and theta 1. So now the important thing comes is defining a good model. That is, what is the good model? So can you tell me, like, if I use a straight line like this, and if I use a second straight line like this, which one is better? Can anyone tell me?
Second one.
Why second one? Why second one is better?
Because sir, it would have more.
Close to the actual data point.
No, that's true, but on what basis you are saying that it is close to the actual data point? What is your mental picture doing in this case? Like, what is the brain thinking about it? Like,
Because it has points on both the sides.
okay,
Because the distance is less. Between the actual points and the predicted line, the distance is less, but this is not in the case of first time.
right. So,
Far away from actual.
right. So this is the actual reason. So basically, this line or the red line, whatever line it is basically we are denoting it by m theta xi. So whatever value that you are predicting on this line is m theta xi. Everybody agrees with this? Like, you feed in the xi to this model, whatever value you will get at this point is m theta xi. So this is the value that you get from the line, and this is the actual actual value, right? So this value is yi, actual value. Okay. So if you want to why you are saying that the purple line is better than the red is because the distance of the error between the yi's and the corresponding, sorry, not like this, yi and the corresponding points for this particular year, the distance, the error that is incurred for the purple line is less compared to the red line for the total number of data points, not for a specific point only, but you have to actually take consideration all the errors that this particular purple line is making with all the points, not only for specific points. So here you might say that this point is closer to the red point, why you are saying that purple line is better? It's not like that. You have to actually incorporate all the contributions of the error this purple line is making with the actual data point, rather and same for the red data points, same for the red line. And what you will observe is that the total number of the total error which the purple line is making is less compared to the red line. Fine. So any questions here?
No, sir.
So if you want to quantify this error, the vertical error which I have written here, it is nothing but it's a m theta xi minus yi, right or not? You are actually taking a distance between the two, like how far a prediction of this particular year is this one and the actual one is this. So the difference between the two is nothing but m theta xi, the model predicting this value, and the corresponding label to that value. So this is the error that is incurred. And what we are trying to do is we are actually trying to measure this error for all the data points. So if I want to measure this error for all the data points, will this equation look like this or not? The one which is written over here, this one, this one. So what we are trying to do, we are trying to calculate the vertical distance error the model is creating m theta xi from the corresponding actual label yi, and we are squaring the error so that all the negatives will become positive, because we want to calculate the total number of loss. We do not want to subtract the losses. We want to add and see how much loss the purple line as well as the red line is making. That's why we are squaring it, and we are summing it for all the samples running from 1 to m. So we are summing up all the samples, and here you can see I is running from 1 to m, which is actually the xi, which is given over here. And then we try to normalize the loss. We do not want loss to be, we want a normalized value of that. So we divide it by the total number of samples. And we keep the factor of 2 also along with that. And this reason will come out later on once I'll discuss and we'll go more into the details that why 2 is coming here. But this way you are actually trying to define a good model, that which model is good, red one is good or purple one is good. And defining a good model is done by quantifying the loss function. So this is the loss function which you are using to quantify which line is good, red or purple. And this argmin theta 0, theta 1 means what is the value of theta 0 and theta 1, which will actually help us in minimizing this loss, this argument. This is basically an argument. So this in short will tell you, like if you write argmin theta 0, theta 1, it means what is the value of theta 0 and theta 1 for the model, because the model is nothing but it is theta 0 plus theta 1 xi 1, right? So we want to train the model, right? So we want to adjust these values of theta 0 and theta 1. So loss will actually try to calculate the value of this, and it wants to calculate which is the optimal value of theta and theta 0 and theta 1, which will reduce the loss to a very small value. And the value for that small value of loss, the value of theta 0 and theta 1 will be the optimal value of that particular model. So here this purple line which is shown over here will have the optimal value of theta 0 and theta 1, and we are writing it by caps on top of it, which denotes that it's an optimal value. Whereas the value of theta 0 and theta 1 corresponding to this red model will not be the optimal one. Any questions here? Any questions?
No, sir.
Okay, good. So today I think time is over, so we will discuss further. We'll go further into the details of this in the next class. Please note that this lecture 1 is still not completed. So once it is completed, then only I will tell you to stop writing for group 1 at least. So group 1 can start drafting their assignments, but I will give you which one will be the group 1 in a while, by today, and by today evening I will tell you which group it is. But they can start drafting this by their own, and I will tell them where to stop. Okay, if there are no questions, then we can close this class today. Okay. Thank you so much for attending the class.